Welcome to CECS 228. Today we're going to continue our counting part 1 set of lecture notes, picking up at generalized pigeonhole principle. So just as a reminder, pigeonhole principle was the idea that if you have k plus 1 objects and you place them into k boxes, then there's going to be at least one box with 2 or more objects. So to generalize that, we think about n objects being placed into k boxes, and well then in that case there's going to be at least one box that contains at least the ceiling of n over k objects. Alright, so to get a better idea of what that principle is saying, let's consider this example 16. If there are 100 people in a meeting room, what does the generalized pigeonhole principle guarantee about the number of people born on the same month? So in this case, the boxes or the categories that we're considering are the months, because we want to know how many people fit into that same birth month. So n is, in this case, let's just think about it as objects and boxes. N is 100, it's representing the people. And then K is the number of categories, which would be the 12 months. Now, in general, that means that pigeonhole principle would guarantee that there would be ceiling of 100 over 12 objects in at least one box, right? So this would be the number of objects placed into at least one box. And so 100 over 12, if you take a look at your calculator, is going to give you 8.33 with the repeating decimals. So the ceiling of 100 over 12 is going to be 9. And that means that there are at least 9 people with the same birth month. Example 17 reads, what is the minimum number of students required in a discrete math class to be sure that at least 6 will receive the same grade if there are 5 possible grades, A, B, C, D, and F? Okay, so again, relating it back to the objects and boxes or the objects and categories, in this case, students are like the objects and the grades are like the categories or the boxes that we are trying to fit the students into. So we know how many categories we have. It's 5 for the different possible letter grades. As far as how many students we are trying to categorize, we don't know. In fact, that is the goal, to find out how many students need to be in the class. What we are given, though, is that at least 6 have to receive the same grade, meaning at least 6 by pigeonhole principle should be the result of taking the ceiling of n over k. Actually, I'll place it over here. Okay, so what can we do at this point? We can start by using this idea that the ceiling of n over k is 6, because that means that n over k has to be at most 6, and it has to be greater than 5, right, in order for this to be true. And then we can also replace in what k is. It's a 5, so we get that 5 is less than n over 5, which is less than or equal to 6. Then we can solve for n by multiplying all 3 parts of the inequality by 5, and we get that 25 has to be strictly less than n, and n has to be less than or equal to 30. So What is the minimum number that n can be? The minimum number would be a 26. So that means that at least 26 students have to be in the class in order to ensure that at least 6 have the same grade. That's the minimum number. Okay, and last example, example 18. What is the least number of area codes that are needed to guarantee that the 25 million phones in a state can be assigned a distinct 10-digit telephone number? And we're going to assume that the telephone numbers are of the form NXX and then NXX and 4 X's, where the first 3 digits form the area code. N represents a digit in the range of 2 to 9 inclusive, so that means it could be 2, 3, all the way through 9. And X represents any digit, so 0, 1, all the way down to 9. Okay. So in order to solve this problem, again, we're trying to look at how many different area codes we need. We should probably take a look at how many different telephone numbers can be generated with that have this format. And then once we've found out what that number is, you can think of those as being categories. And the 25 million phones that need to be assigned a phone number are like the objects. Okay, so here I'm just going to write that N is the number of phones that need a phone number. And well, that's 25 million, or 25 times 10 to the 6. Now K is the category, meaning the phone number that they receive, that they're assigned to. So this is the number of phone numbers that have the form NXX XXX. Okay. So if we can find out how many phones are in each category, meaning they get assigned the same number, then we know how many area codes need to be produced in order to make sure that that 7-digit number is preceded by a unique 3-digit number, so that altogether the 10 digits are unique. Okay, so let's see. So then the ceiling of n over k is going to be the number of phone numbers, the number of phones assigned the same 7-digit number which also equals the number of area codes that are needed. All right, so we already have n. We just need to find out what is k. So what is k? Well, we have n is of the form, or can have a digit 2, 3, all the way through 9. So essentially, it could have 9 different digits, or 8 different digits, I should say. So there is 8 possibilities for the first digit. Then there are 10 possibilities for every other digit, because it could be a 0, 1, 2, all the way down to 9. And so we have an 8 times a 10 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 times a 10. So 4 times. Okay. That gives us an 8 times a 10 to the 6. Alright, so now that we have all that information, we can use generalized pigeonhole to find to find the number of phone numbers that are given the same 7-digit number, and that's going to be the ceiling of 25 times 10 to the 6 divided by 8 times 10 to the 6. The 10 to the 6's cancel out, they divide out to 1, so we're really just looking at the ceiling of 25 over 8. And 25 over 8 is going to give you something like 3.1 something, so that means that the ceiling will be 4. Or in other words, we need at least 4 area codes. This brings us to counting part 2, which deals with permutations and combinations. So all of the principles that we've learned thus far, the product, sum, division, inclusion, exclusion, and pigeonhole principles, are now going to be applied to help us find how many different ways can we select a particular number of elements. And so we're going to start with what is the definition of a permutation. So a permutation of a set of distinct objects is an ordered arrangement of those objects. And if you take a look here at figure 1, we have 3 elements, 1, 2, and 3. And if we consider all of the different ways to arrange those 3 elements, then each one of those arrangements is called a permutation. Now it is possible to take only part of the elements and permute those. In that case, we call those R permutations, where R is the number of elements that you're taking from the whole set. So for instance, let's say that you want to consider all of the 2 permutations of the numbers 1, 2, and 3. That means that we're taking 2 elements and permuting them. So if we start by taking 1 and 2, we can have the arrangement 1, 2, or 2, 1. Then we can take the combination 1 with 3 and permute that. So we would have 3 with 1 or 1, 3. Those would be the 2 arrangements. And then the final combination would be elements 2 and 3, of which we have the arrangements 2, 3 or 3, 2. So that brings us to a final answer of 6 possible 2 permutations of the elements 1, 2, and 3. Okay. So with that same kind of idea in mind, we're given now the set of elements A, B, C, and we're being asked what are all the permutations of the set S, meaning what are all the permutations of all the elements. And so the way that we can construct them is we can start by fixing one element, say A, and then permuting the last 2 elements. So B and C would be one possible arrangement, but then C with B at the end would be a second possible arrangement. And beyond those 2 permutations, there are no other ones that start with an A. So now we consider fixing another element at the beginning of the permutation. So say B. That leaves A and C available for permuting or moving around, rearranging. So we could have B with AC or B with CA. And finally, we can fix C at the beginning, leaving AB at the end to permute. So we have an arrangement CAB or CBA. And so those would be all the permutations, because now at this point, we've considered all possibilities of elements being the first element. Now, what are all the 2 permutations of the set S? Well, first we have to think about what are the different combinations that we can have for those 3 elements, combinations of 2 elements, that is to say. So I could take A with B, for instance, and then that would result in a permutation B with A of those two elements. Then I could take a combination of A with C and permute those. And finally, we can take a combination of B with C and permute those. And so at that point, we have paired all the possible pairings of two elements and their permutations. Okay, so we have 6 two permutations of the set. Okay, let's think about example 2 now. In how many ways can we select 3 students from a group of 5 students to stand in line for a picture? And then in how many ways can we arrange all 5 of these students in line for a picture? So if they're standing in line, the order in which they stand is important. So let's say, just so that we relate it back to the set, let's say that we have set S, which consists of student 1, student 2, 3, 4, and 5. And from this set, we want to select 3 students initially. So we're focusing on the first question. In order to select 3 students, we would have to think of all the combinations that we can have from those 3 students out of the 5. But just to make it simpler on ourselves, we can use the product principle and think about, well, for the first place in the line, we have 5 options of placing a student. And then once we've placed that student, we would have 4 remaining options for second place in line. And then for third place in line, we would have 3 students left to pick from. So the final number of ways to pick 3 students to stand in line would be 60. So this would correspond to all 3 permutations. Okay. Now for the second part, they want us to find out in how many ways we can arrange all 5 of these students in line. So that would be just the number of all permutations of S. Okay, and again, applying that same principle, the product principle, for first place we would have 5 students, then for second place we would have 4, then 3, then 2, and by the time we get to the last place in the line, there's only 1 student left who can occupy it, so there's only 1 choice. And if we take the product of all these, we would have basically 5 factorial, right? If we multiply all the integers from 1 up to 5, that is simply 5 factorial. And so that is going to give us, well, let's see, this is 20 times a 3, that's a 60, times a 2, that's a 120, times a 1, that's still just a 120. So there's 120 ways of selecting 5 out of 5 students. And here the order matters. Okay. So one thing that I'd like for us to just observe is in the case here of the 3 permutations out of 5 students, if we were to generalize that idea of just finding maybe like the number of R permutations, well, that would be n options for the first place in line, and then for the next one we would have n minus 1, And if we're picking r of them, then we want to find out what would this integer be. Well, to find out what that would be, let's just think about how many are left over. If the number of positions, or the total number of students, I should say, is n, that means that we are leaving out of the what would be the factorial. We're leaving out n minus r elements, right? So here we would have n minus r. Here we have r elements. So if this were a factorial, we would have 1, 2, 3, all the way down to n minus r. And then that means that this would begin at n minus r plus 1, and then continue all the way to n, right? But because we're only picking r of them, these n minus r elements are forgotten, and we only multiply from n minus 1, and down to n minus r plus 1. So the number of r permutations is ultimately that. It's n times n minus 1 times all the way down to n minus r plus 1, which is sometimes written as an n minus an r minus 1. And that's in fact what the theorem on page 3 tells us. It reads, if n is a positive integer and r is an integer that is less than or equal to n but greater than or equal to 1, then there are n times n minus 1 times n minus 2 all the way down to n minus r minus 1 r permutations of a set with n distinct elements. And so the way that we denote this a little bit more compactly is we write p of n comma r, where again n is the number of distinct elements and r is the number of elements that we are picking out of out of n and permuting. Now the corollary says that number p of n comma r can be written as n factorial over n minus r factorial. And we're going to show that it's a very short proof, so we're going to write it down here. From the theorem, we have that p of n comma r is n times n minus 1 times n minus 2 times all the way down to an n minus r plus 1. I'm simply going to distribute the negative here. So if we were to continue to multiply the next terms, it would be n minus r times n minus r minus 1 all the way down to times 3 times 2 times 1. But we can't simply multiply, right, to this quantity, because otherwise it's no longer the same value. So at the same time, we're going to be dividing by these factors. So n minus r times n minus r minus 1 times all the way down to 3, 2, and 1. So essentially we're multiplying by a 1, but it's in the form of these products. Okay, so what happens in the numerator? In the numerator, we're now multiplying every integer from n all the way down to 1. So that's simply n factorial. And in the denominator, we're multiplying all of the integers from 1 all the way up to n minus r. So this is n minus r factorial. And that is the claim of the corollary, that the number of r permutations will be given by n factorial over n minus r factorial. Okay, so now we're going to apply that with example number 3. How many ways are there to select a first prize winner, a second prize winner, and a third prize winner from 100 different people who have entered a contest? So if we use the theorem by itself, this would be p of 100 comma 3, right? We have 100 people, and we have 3 people that we want to pick out of those 100 people to give them first, second, and third place. So that means that there's 100 options for first place times 99 options for second times 98 options for third. And if we punch that into our calculator, we're going to get 970,200. Now, if you want to use the corollary, because here essentially what we did was apply the theorem, if you want to use the corollary, you would, so this is by the theorem, and this is using the corollary, you're going to end up having the same thing. This would be a 100 factorial divided by an n minus r. So this is n, this is r. 100 minus 3 will give us 97 factorial. So essentially you're going to end up with 100 times 99 times 98, and everything else, 97 through 1, is going to cancel out with the denominator. But if you want to punch it into your calculator, you can do so. The factorial is in in most calculators. So once you've calculated that, you'll see that it's 970,200. Example number 4 is very similar to example 3. It reads, suppose that there are 8 runners in a race, and the winner receives a gold medal, the second place finisher receives a silver medal, and the third place finisher receives a bronze medal. How many different ways are there to award these medals if all possible outcomes of the race can occur, and there are no ties? Okay, so again, in this case, we're looking at 8 runners, and out of those 8 runners, we need to pick 3 winners, the winner of the gold, silver, and bronze. So that is 8, pick 3, so this is going to be 8 options for the first place, or the gold medal, times 7 options for the second place, the silver medal, times 6 options for the third place, or bronze medal. So that is going to bring us to 336 possible ways, or possible outcomes for the race. Example 5 is asking us how many permutations of the letters A, B, C, D, E, F, G, and H contain the string ABC. So what we want to do is, instead of thinking about all of the letters individually, we can go ahead and group A, B, C as one string. And so that way we just permute all the other letters, and A, B, C, we want to see how many different ways are there or how many different strings exist with the D, E, F, G, H permuted and the A, B, C sticking together, and of course appearing at different position amongst the rest of the letters. Okay, so we're going to consider A, B, C as being one object. Since we want them to stay together as part of the permutation. Okay, and so what that means is that we really have 1, 2, 3, 4, 5, 6 different positions in which we are going to be placing letters. So for this first position, we'll have 6 options. For the second position, we'll have 5, then 4, 3, 2, and 1. Or in other words, this is the same as having 6 elements, and we're going to be permuting 6 out of 6. So that's a 6 factorial, which is going to turn out to be, well, this is 30, This is going to be 120. This is going to be a 360. And times 2, that's going to be a 720. Okay. And example 6, suppose that a saleswoman has to visit 8 different cities and she has to begin her trip at a specified city, but she can visit all the other 7 cities and cities in any order that she wishes. How many possible orders can the saleswoman use when visiting these cities? Um, okay, so in this case, we have 8 cities, but the first one, there's no, basically there's no option. She has to start at a specific one. For the remaining 7, she can do whatever she wants. So there'll be 7 options for cities, for the first city to visit. Then there will be 6 options for the second, 5 for the third, so on and so forth. Okay, so this is the same as 7 factorial, or in other words, it's as if we only have 7 elements and we are picking, or we're permuting all 7 of them. So 7 factorial, that is going to be a 7 times 720, which will give us 5,040 ways of visiting the cities. Next, we're going to consider combinations. So a combination of a set of distinct objects is an unordered arrangement of these objects. So basically, it's a subset of the set. In particular, an unordered arrangement of R elements of a set is called an R combination. So if we compare against permutations, in a permutation, the order matters, right? So if we have the arrangement 1, 2, 3, that's different from the arrangement 1, 3, 2. In a combination, that doesn't matter. So that means that there really is only one way to combine all 3 elements, and that is to pick all 3, right? 1, 2, and 3, and the order doesn't matter. If we're considering the 2 combinations in contrast to the 2 permutations, we could pick a combination of 1, 2, and then consider the different arrangements of 1 and 2, which are just 1, 2, and 2 and 1. In a combination, these would be considered the same. The order wouldn't matter. So the number of 2 combinations will be less than the number of two permutations. Right? We'll only have 1 combined with 2, or 1 combined with 3, or 2 combined with 3. Right, so let's look at some applications of that idea. How many different committees of 3 students can be formed from a group of 4 students? So we have, let's say, a set S consisting of student 1, 2, 3, and 4. And we want all combinations of 3 students only. So one possibility could include a student 1, so I'll call that the first subset, contains student 1, and we could have student 1 combined with student 2 and student 3. Another one could be student 1 combined with, oops, that should be 1, student 2 and student 4. Then we could have student 1 combined with student 3 and student 4. And then at that point, we've pretty much have all of the sets that could include student 1. We next consider all the combinations that include student 2 that haven't already been considered in these first three subsets. Okay, so we can have student 2 combined with student 3 and student 4. And then, well, that would be pretty much, let's see, that would be pretty much it, because all the other combinations that include student 2 would also have to include student 1, right? Like for instance, if I do student 2 with student 1 and student 3, that's already accounted for here. Or if we take student 2 with student, let's say student 1 and student 4, that's already accounted for here. So we only have 4 possible subsets that take 3 elements from the set S. And so one thing that I would like you to notice is just in regards to counting. And let me just write the final answer to this. There are 4 different 3 combinations of 4 students. But just in terms of counting, so that because listing all these elements would get tedious if the set were any bigger, right? So just in terms of counting, let's think about how we can come up with a formula for these R combinations. Well, we can first think about how many different ways are there to pick 3 students out of 4, right? So there are P of 4 comma 3 ways to order 3 students out of 4. But out of those, out of these many ways, P of 4 comma 3, we want to divide out the number of permutations that exist amongst 3 elements. Okay, so there are P of 3 comma 3 ways to permute 3 elements. Okay. So hence, the number of R combinations is going to be the number of permutations of 3 out of 4 divided by the number of ways that you can permute 3 elements, because all of those are going to correspond to the same subset, right? So hence, the 3 combinations of 4, which I'm going to go ahead and write as C4 comma 3, is going to be the number of permutations, the number of 3 permutations out of 4 divided by the number of 3 permutations out of 3. Right, so for instance, if they ask us how many different 2 combinations of the sets are there for A, B, C, D, well, we can say this is 4 elements. So 4, we're going to choose 2 out of the 4 is going to be the same as taking the 2 permutations out of 4 and dividing by the 2 permutations out of 2, or the number of ways to permute 2 elements. Yeah. And this we saw is 4 times 3 divided by a 2 times 1, or in other words, a 12 over 2, which is a 6. Now, what are they? That's the second part. Well, we want to take subsets of size 2. The first subset can be A with B. Then we can take A with C, and finally A with D. Then we can take B with C, B with D, and that would be it for subsets that contain B. Then we can consider C with D, and well, at that point, if we try to consider what are all the subsets that have D, we would have to think back to elements that came before it. So like C with D, or D with B, or D with A. But those are all accounted for because we considered them when we constructed the subsets that included earlier elements. So if we now count how many of those subsets are there, there are 6, the same number that we got simply by that counting kind of mindset that we developed earlier. Okay, so that is what this next theorem reads. The number of R combinations of a set with n elements where n is a non-negative integer and R is an integer between 0 and n is n divided by R factorial times n minus R factorial, which is sometimes also expressed as n choose R. Yes, I'll just write it. This is read as n choose R. And this is called a binomial coefficient, which is just standing in short for this n factorial divided by R factorial times n minus R factorial. Okay. So let's see. Let's try to apply that formula now to example number 9. How many different 3 combinations of the set 1, 2, 3, 4 are there, and what are they? So we have we have 4 choose 3, which is going to be a 4 factorial divided by a 3 factorial times a 4 minus 3 factorial, or in other words, a 4 factorial over 3 factorial times a 1 factorial. And that would be a 4 times 3 times 2 times 1 divided by a 3 times 2 times 1 and then times 1 for this 1 factorial. So all of these are going to divide out to 1. We're going to end up with 4. And what are they? Well, we can start by taking the combination 1, 2, and 3. Then we could do 1, 2, and 4. Then we could take 1, 3, and 4. And finally, we could take 2, 3, and 4. Okay, so the way that I start constructing these subsets is I first fix maybe like the first 2 elements and then consider what are the options for the last element. So one of them is a 3 and then the other one is a 4. Then I fix another 2 different elements, let's say like 1 and 3, and I think about what are the options for the last element. Well, it could be a 2, but in that case we would have the 1, 2, 3 that was already written. Or we could have a 4, which has not been written before. So then we take that subset 1, 3, 4. And then after that, I fix the 1 with the, the 2 with the 4, and I consider, well, what is the option, sorry, not the 2 with the 4, the 2 with the 3, and then I consider what's the option for the third element. Well, we have 1, but again, we already have that subset, or we have 4, and that would be a new one, so that we write that combination down. From there, if you attempt to build any other subset, it's just going to be a repetition of one of the earlier ones that we wrote down because it considers earlier elements. So these would be all the 4 combinations. And if you would like to go ahead and think about what are all other subsets that you can consider starting with 4, you'll see that they're already listed. All right, example 10. How many poker hands of 5 cards can be dealt from a standard deck of 52 cards? Also, how many ways are there to select 47 cards from a standard deck of 52 cards? Okay, so the total number of elements that we have is 52, and we're choosing 5 out of those cards. And so according to our theorem, that means that we would have 52 factorial over 5 factorial times a 52 minus a 5 factorial. Okay, so that is a 52 factorial over 5 factorial times 47 factorial. And that means that we would have 52 times 51 times 50 times 49 times 48 times 47 all the way down to 1 over 5 times 4 times 3 times 2 times 1 times 47 times 46 times all the way down to 1. So basically all factors 47, 46 to anything that is smaller will divide out to 1 because of this 47 factorial. And the only thing that'll survive is this 52 through 48 divided by the 5 factorial. So if you do a little bit of math on that, we're going to get 2,598,960 different ways of dealing 5 cards. Okay, so that's the first part. The second part, I guess I'll label it 1 and 2. The second part is asking how many different ways are there to deal 47 out of the 52 cards. So that would be 52 choose 47, and that means that we have 52 factorial divided by a 47 factorial times a 52 minus a 47 factorial. So that's a 52 factorial over 47 factorial times 5 factorial. And as you can see, these two are the same, essentially. We've just changed the order of these two factors, which doesn't really matter. So in the end, we're still going to get the same value. So there are also 2,598,960 ways of dealing 47 cards out of a standard deck with 52 cards.